Hello and welcome. Tonight, we're going to explore something wonderfully simple, yet beautifully complex. We're going to watch a candle burn, and we're going to understand, in quiet detail, exactly what's happening as that small flame dances in the darkness. There's no rush here, no urgency, just the slow, patient unfolding of scientific truth. The kind of truth that's been hiding in plain sight for thousands of years, in every candle that's ever been lit. So settle in, get comfortable, let your breathing slow, and let's begin our journey into the gentle science of fire and wax. Before we strike a match, let's simply look at our candle. Let's appreciate what it is before it becomes something else. A candle in its unlit state is, at its most basic, a solid piece of wax surrounding a cotton wick. That's all. Simple, unassuming. Yet within this simple object lies a carefully balanced system, refined over centuries. The wax itself. Let's think about the wax for a moment. If you've ever held a candle, you know the texture. Smooth, slightly waxy, obviously. At room temperature, it's solid, but not hard like stone. You can press your fingernail into it and leave a mark. This tells us something important about its molecular structure. Most candles today are made from paraffin wax. Paraffin is derived from petroleum, though that's a relatively recent development in the long history of candle making. For thousands of years, people used whatever was available: beeswax, tallow from animals, bayberry wax. Each had its own properties, its own scent, its own way of burning. But let's stay with paraffin for now, because it's what most of us encounter. Paraffin wax is a hydrocarbon. That means it's made of hydrogen and carbon atoms, linked together in long chains. Picture a chain, if you will. Each link is an atom, and these links go on and on, perhaps 20 carbon atoms long, perhaps 30, perhaps more. These long molecular chains are what we call alkanes. They're saturated hydrocarbons, meaning every carbon atom is bonded to as many hydrogen atoms as it can hold. No double bonds, no triple bonds, just single bonds throughout, stable and unremarkable. And here's what makes paraffin solid at room temperature. These long chains lie next to each other, somewhat organized, somewhat parallel. They're attracted to each other through weak forces called van der Waals forces. These forces aren't chemical bonds, not in the traditional sense. They're more like gentle suggestions, slight attractions between the electrons in one molecule and the nuclei in another. It's like a crowd of people standing close together on a cold day, each person seeking the warmth of others, but not actually holding hands. The force keeping them together is present but subtle. At room temperature, these van der Waals forces are strong enough to keep the paraffin molecules more or less in place. The wax maintains its shape. It has structural integrity. But warm it up a bit, give those molecules some energy, and they start to slide past each other. The van der Waals forces begin to weaken. The wax softens. Warm it up more, and eventually the molecules move freely. The wax melts. It becomes a liquid, but we're getting ahead of ourselves. For now, the candle sits at rest. The wax is solid. The long chains are arranged in their gentle, parallel fashion, held together by those whisper-quiet intermolecular forces. And then there's the wick. The wick is typically made of cotton. Cotton is cellulose, which is also a long chain molecule, but very different from paraffin. Cellulose is a carbohydrate, a polymer of glucose molecules. If you could see it at the molecular level, you'd see ring structures linked together, forming long, strong fibers. Cotton fibers are excellent for wicks because they're absorbent. They have tiny spaces between the cellulose molecules, tiny capillaries that can hold liquids. This property becomes crucial once the candle is lit. The wick has usually been treated or primed before being placed in the candle. Sometimes it's been soaked in wax itself, sometimes in salt solutions, sometimes in other chemicals. The treatment helps the wick burn at a controlled rate, prevents it from burning too quickly or producing too much smoke. A proper wick is a marvel of simple engineering. It needs to burn slowly enough that the wax can melt and vaporize, but not so slowly that the flame drowns in liquid wax. Too thick, and the flame can't get enough fuel. Too thin, and it burns away before the wax can feed it properly. Everything in a candle is about balance, equilibrium, the right materials in the right proportions, working together in a careful dance that's been choreographed over millennia. And so, our candle sits, waiting, potential energy stored in those hydrocarbon chains, ready to be released. The wick stands ready, prepared to conduct melted wax upward toward the flame that doesn't yet exist. Everything is still, everything is quiet, everything is in a state of patient anticipation. And now, we strike a match. The match head scrapes against the striking surface. Friction generates heat. The chemicals in the match head, potassium chlorate, phosphorus, sulfur, depending on the type of match, react with this heat. A small flame appears at the end of the matchstick. This flame is already fascinating in its own right, but we're here for the candle. We bring the match flame to the wick. We hold it there for a moment. 1 second, 2 seconds, 3. What's happening during these few seconds? Heat from the match flame is transferring to the wick and the wax immediately surrounding it. Heat is energy, molecular motion. The molecules in the wick begin vibrating more rapidly. The cellulose structure doesn't change yet, but it's being energized. More importantly, the wax at the top of the candle, right around the wick, begins to melt. Remember those van der Waals forces? The gentle attractions between molecules? The heat from the match is giving the wax molecules enough energy to overcome these forces. The molecular chains begin to slide past each other. Solid becomes liquid. This melted wax does something remarkable. It moves. It rises up through the wick. Capillary action. That's the term. Capillary action is the ability of a liquid to flow in narrow spaces without the help of gravity, sometimes even against gravity. It happens because of adhesive forces between the liquid and the surface it's touching, combined with cohesive forces within the liquid itself. The wick, made of cotton fibers, is full of tiny spaces between those cellulose molecules. These spaces act like thousands of microscopic tubes. The melted wax is attracted to the cotton fibers. There's a slight polarity interaction happening at the molecular level. This attraction pulls the liquid wax up into the wick. At the same time, the wax molecules are attracted to each other through those same van der Waals forces we discussed earlier. So as some wax molecules move up the wick, they pull their neighbors along with them. It's a chain reaction of gentle pulling. The wax climbs up the wick, slowly, steadily, rising toward the point where the match flame is being held. And then something crucial happens. The wax at the very top of the wick, right at the point of the flame, gets hot enough to vaporize. Vaporization is a phase change, like melting, but more dramatic. Melting turns a solid into a liquid. Vaporization turns a liquid into a gas. It requires more energy because the molecules need to separate from each other almost completely, to break free from even those weak van der Waals forces and move independently through space. So now, we have paraffin molecules in their gaseous form. These molecules are free-floating, moving rapidly, full of energy, and they're in the presence of a flame, which means they're in the presence of heat and oxygen. What happens when a hydrocarbon encounters oxygen at high temperature? Combustion. Fire. The release of the potential energy stored in those carbon-hydrogen bonds. The paraffin vapor molecules react with oxygen molecules from the air. The chemical bonds break and reform. Carbon dioxide is produced. Water vapor is produced. And energy is released in the form of heat and light. The reaction is exothermic, meaning it produces more heat than it requires to keep going. This heat melts more wax travels up the wick, more wax vaporizes, more combustion occurs. A cycle has been established, a feedback loop. The candle is now self-sustaining. We can remove the match. The candle flame continues on its own. It has everything it needs: fuel from the wax, oxygen from the air, and heat from its own combustion to keep the process going. The flame settles into its characteristic teardrop shape. And now, we can really begin to examine what we're seeing. Look at a candle flame. Really look at it. Don't just glance and move on. Give it your full attention for a moment. What do you see? Most people would say they see a yellow flame, perhaps with some blue at the bottom, and they'd be right. But there's so much more happening than that simple description suggests. A candle flame has zones, distinct regions where different things are occurring. These zones aren't always sharply defined. Flames are dynamic, fluid things, but they're there, and each plays a specific role in the combustion process. Let's start at the bottom, where the flame meets the wick. The very base of the flame, right where it touches the wick, is actually dark. Not black, but darker than the rest of the flame. This is the fuel-rich zone, sometimes called the reduction zone. Here, the wax vapor is being produced, but there isn't enough oxygen yet for complete combustion. The temperature is around 600 to 800 degrees Celsius. Hot, certainly, but not the hottest part of the flame. The wax molecules are breaking apart, but not yet fully reacting with oxygen. If you could peer into this zone at the molecular level, you'd see chaos. Carbon-carbon bonds breaking, hydrogen separating, free radicals forming. Those are molecular fragments with unpaired electrons, highly reactive and short-lived. It's a preparatory phase, setting the stage for what comes next. Just above this dark zone, there's often a thin blue layer, especially noticeable in the darkness. This blue color is significant. Blue flame indicates complete combustion. It means that hydrocarbon molecules are reacting with oxygen efficiently, with plenty of oxygen available. The temperature here is higher, around 1,400 degrees Celsius. The blue color itself comes from excited carbon monoxide molecules. When carbon and oxygen combine to form CO, they release energy. Some of this energy excites the electrons in the CO molecules to higher energy levels. When these electrons fall back down to their normal state, they release that energy as light. The wavelength of this light happens to fall in the blue part of the spectrum. But here's something interesting. Most candle flames don't show much blue. The blue zone, if present, is usually very thin, sometimes barely visible. Why? Because most of the combustion in a candle flame is incomplete combustion. As we move up from the blue zone, we enter the luminous zone. This is the large, bright, yellowish part of the flame that most people picture when they think of candlelight. This is the warm glow that lights up a room. The luminous zone is where incomplete combustion is occurring. There's plenty of fuel vapor rising from the wick, but there isn't quite enough oxygen to burn it all completely. So what happens? The hydrocarbon molecules break apart. But instead of immediately reacting with oxygen to form carbon dioxide and water, they form something else first. Soot. Soot is carbon. Tiny particles of carbon. When hydrocarbons don't have enough oxygen for complete combustion, the carbon atoms clump together. They form little specks, solid particles suspended in the hot gases of the flame. These carbon particles are what makes the flame glow yellow. Here's how it works. The tiny carbon particles are heated by the combustion reactions happening around them. They get extremely hot, hot enough to emit thermal radiation. This is black body radiation, the same principle that makes a piece of metal glow red when heated, then orange, then yellow, then white as it gets hotter and hotter. The soot particles in a candle flame are heated to around 1,000 to 1,200 degrees Celsius. At this temperature, they emit light predominantly in the yellow and orange part of the spectrum. That's the warm candlelight we know and love. Eventually, as these carbon particles drift toward the outer edges of the flame, they do find enough oxygen. They complete their combustion, turning into carbon dioxide. That's why soot doesn't continuously pour out of a properly burning candle. Most of it burns up before leaving the flame, but not all of it. A small amount does escape, which is why if you hold a plate above a candle flame, it will gradually collect a layer of black soot. Finally, there's the outer zone of the flame. This is sometimes called the non-luminous zone, or the oxidizing zone. It's nearly invisible, just a slight shimmer in the air around the bright yellow flame. This is the hottest part of the candle flame. Temperatures here can reach 1,400 degrees Celsius or higher. This is where any remaining fuel vapor encounters abundant oxygen from the surrounding air. Complete combustion happens here. Carbon dioxide and water vapor are the main products. This zone doesn't glow brightly because there aren't many soot particles here. The combustion is too efficient, too complete. The particles that do exist are so thoroughly oxidized that they don't get a chance to heat up and emit that warm yellow light. So, we have these zones, these regions of different chemistry and different temperatures. all existing simultaneously in a space that's perhaps only a few centimeters tall. It's a miniature ecosystem of fire, each part dependent on the others, all working together to transform solid wax into light and heat. And all of it, is happening because of that simple chemical principle we mentioned earlier. Hydrocarbons plus oxygen plus heat equals carbon dioxide, water, and energy. The elegance of it is really quite beautiful when you stop to think about it. While the flame dances above, something equally important is happening below. The wax at the top of the candle is melting. It's forming a pool of liquid, a small reservoir surrounding the base of the wick. This wax pool is not just a byproduct of the burning process. It's an essential component. Without it, the candle wouldn't work. The heat from the flame radiates downward. Remember, heat moves in three ways: conduction, convection, and radiation. All three are at play here. Conduction is heat transfer through direct contact. The flame heats the upper part of the wick, and this heat conducts down through the cotton fibers to the wax immediately surrounding the wick base. Convection is heat transfer through the movement of fluids. The hot gases from combustion rise because hot air is less dense than cool air, and cooler air moves in to replace them. This creates air currents around the flame. These currents also carry some heat downward toward the candle surface. Radiation is heat transfer through electromagnetic waves. The flame emits infrared radiation heat you can feel even without touching the flame. This radiant heat spreads outward in all directions, including downward toward the wax. All of this heat is absorbed by the wax at the top of the candle. As the wax absorbs energy, its temperature rises. When it reaches the melting point, typically around 37 to 65 degrees Celsius for paraffin wax, depending on the exact formulation it undergoes, that phase change we discussed earlier, solid becomes liquid. The wax pool forms. If you watch a candle carefully, you'll notice the wax pool develops gradually. At first, immediately after lighting, there's barely any liquid. The flame is doing all it can just to maintain itself. But as minutes pass, the pool expands. It grows wider, reaching outward toward the edges of the candle. The size and shape of this pool depends on several factors: the diameter of the candle, the type of wax, the thickness and material of the wick, the ambient temperature of the room. All of these variables influence how much wax melts and how far the liquid spreads. A well-designed candle will develop a wax pool that reaches nearly to the edge of the candle's diameter, but not quite. You want the entire top surface to liquefy for even burning, but you don't want the liquid to overflow the edges. That would be wasteful and potentially messy or dangerous. This is why candle makers carefully match wick size to candle diameter. A wick that's too small won't generate enough heat to melt the wax all the way to the edges. You'll get a tunnel effect, where the candle burns straight down the middle, leaving walls of unmelted wax on the sides. A wick that's too large might generate so much heat that the wax pool becomes too deep, potentially drowning the flame or causing the candle to burn too fast. Balance. Again, it's all about balance. The depth of the wax pool is also important. Typically, it's only a few millimeters deep. Deep enough to provide a reservoir of fuel, shallow enough that the wick can still draw it up efficiently through capillary action. And that liquid wax is constantly moving in subtle ways. It's not static. There are gentle convection currents within the pool itself. Wax directly around the wick is hottest. It's closest to the flame and the base of the wick. This hot wax is slightly less dense than the cooler wax, farther from the wick. So the hot wax near the wick tends to rise slightly and spread outward along the top surface of the pool. Meanwhile, cooler wax from the edges sinks slightly and moves inward to replace it. It's a very slow circulation, almost imperceptible, but it's there. This circulation helps distribute heat throughout the wax pool. It helps maintain a relatively uniform temperature in the liquid wax, which helps ensure consistent wicking and consistent fuel supply to the flame. Meanwhile, at the surface of the wax pool, some vaporization is occurring even from the liquid. Not much. Most of the vaporization happens up in the wick, right at the flame. But some wax molecules at the liquid surface do gain enough energy to escape into the air. You can often smell a candle even when you're not right next to it, and this is part of why. Fragrance molecules, or just the scent of the paraffin itself, are evaporating from the warm liquid. The edge of the wax pool where liquid meets solid is constantly shifting. As the candle burns, more solid wax melts and joins the pool. The liquid edge creeps outward. Eventually, when the candle is extinguished and cools down, this liquid wax will solidify again. If the candle is burned properly, the entire top surface should have melted and then re-solidified, leaving a smooth, flat top ready for the next burning session. But that's for later. For now, the pool remains liquid, gently rippling with those subtle internal currents, continuously supplying fuel to the wick above. Let's return our attention to the wick itself, because it's undertaking a remarkable journey as the candle burns. When we first light a candle, the wick is coated in wax. As we discussed, it may have been primed with wax during manufacturing. And even if it wasn't, within seconds of lighting, the melting wax from the candle top coats it. The cotton fibers of the wick are hygroscopic, meaning they readily absorb liquids, but they're also burning. The very tip of the wick is actively combusting, turning to ash. So, the wick exists in a strange state. It's simultaneously a fuel source, a fuel delivery system, and a self-consuming structure. The tip of the wick, in the flame, is incredibly hot. The cellulose molecules that make up the cotton are breaking down. Combustion is occurring. Carbon dioxide and water vapor are produced. The cotton fibers turn into ash. If you look closely at a burning candle, you can often see this ash at the tip of the wick. It's black, crumbly, sometimes with a slight orange glow. This is the carbonized remains of the cellulose, the parts that haven't yet blown away or fully combusted. But here's what's clever. The wick burns slowly, much more slowly than a piece of cotton string would burn if you just set fire to it in open air. Why? Because the wick is being continuously cooled by the liquid wax it's drawing up from below. Think about it. Liquid wax is flowing up through the wick via capillary action. This wax is hot. Yes, it's around 50 to 70 degrees Celsius or so, but that's far cooler than the temperature of the flame, which is over 1000 degrees. So this relatively cool liquid is flowing up through the wick, absorbing heat as it goes, keeping the wick from burning too quickly. It's a self-regulating system. If the flame gets too hot, more wax melts. More liquid flows up the wick. This increased flow carries away more heat, cooling the wick slightly, preventing it from being consumed too quickly. If the flame gets too cool, less wax melts. Less liquid flows up the wick. With less cooling, the wick gets slightly hotter, which increases the vaporization of the wax at the tip, which makes the flame grow slightly. The system finds its equilibrium. As the candle burns over hours, the wick gradually gets shorter, but not as short as you might expect. Some of the wick is consumed by combustion, yes, but some of it is also preserved, encased in solidified wax on the sides of the candle as the top surface burns down. This is why, when you look at a partially burned candle that's been extinguished and cooled, you often see a charred wick sticking up a short distance above the wax surface. That blackened tip is the part that was in the flame, turned to charcoal. Below it, encased in wax, is the rest of the wick, protected and preserved for the next lighting. Traditional candle makers understood all of this intuitively. Even if they didn't know the chemistry, they knew that wick size mattered. They knew that certain types of cotton worked better than others. They knew that sometimes you need to trim the wick before lighting, especially if it's gotten too long. A wick that's too long will produce a flame that's too large, too tall. The flame will flicker and smoke. Too much wax vapor will be produced, more than can burn completely in the available oxygen. Soot will escape into the air. A wick that's too short might struggle to draw up enough wax. The flame could be small, weak, possibly drowning in liquid wax if the pool is too deep. Modern candles often use wicks that are designed to be self-trimming. These are wicks that curl slightly as they burn, bending the tip over into the outer zone of the flame where it's hottest and most oxygen-rich. This ensures that the ash at the tip burns away cleanly, preventing the wick from growing too long. It's a small detail, but it's one of many small details that make modern candles so reliable. You can light a good candle and let it burn for hours with minimal attention, confident that it will maintain a steady flame. We've mentioned several times that burning a candle involves reacting hydrocarbons with oxygen. But let's slow down and really examine what that means at the molecular level. Paraffin wax is a mixture of hydrocarbons, but let's use a simple example, hexacosane. That's a hydrocarbon with 26 carbon atoms in a chain, a component commonly found in paraffin. Its chemical formula is C26H54. Each molecule of hexacosane contains 26 carbon atoms and 54 hydrogen atoms, all connected by single covalent bonds. These bonds represent potential energy, stored in the arrangement of electrons. When hexacosane burns, when it combusts, it reacts with oxygen. The balanced chemical equation for complete combustion looks like this: 2C26H54 plus 79O 252 CO 2 plus 54 hours 20. Let's pass this slowly. 2 molecules of hexacosane react with 79 molecules of oxygen. This produces 52 molecules of carbon dioxide and 54 molecules of water. Those are big numbers. 79 oxygen molecules for just 2 hydrocarbon molecules. This tells us something important. Combustion requires a lot of oxygen. The air around a candle flame must continuously supply this oxygen, or the flame will go out. But what's actually happening during this reaction? How do we get from reactants to products? It's not a simple one-step process. Combustion is a complex series of reactions, involving many intermediate steps and short-lived molecular fragments. First, the heat of the flame breaks some of the carbon-carbon and carbon-hydrogen bonds in the hydrocarbon molecules. This requires energy, which is provided by the heat already present in the flame from previous combustion. This is called the initiation step. When these bonds break, they form free radicals. For example, a CH bond might break to form a carbon-centered radical and a hydrogen atom. These radicals are extremely reactive. They have unpaired electrons, and nature abhors unpaired electrons. These radicals then react with oxygen molecules in the air. Oxygen is good at this. It's an oxidizer, eager to accept electrons and form bonds. When a hydrocarbon radical reacts with oxygen, it can form various intermediate compounds: peroxy radicals, aldehydes, ketones, and others. These intermediate compounds are unstable. They quickly undergo further reactions, breaking apart, rearranging, reacting with more oxygen or with other radicals. It's a cascade of chemical changes, happening incredibly fast, at molecular speeds. Eventually, through this series of steps, we arrive at the final products: carbon dioxide and water, CO2 and H2O. These are stable molecules. The carbon has achieved its most oxidized state. The hydrogen has bonded to oxygen. No more energy can be extracted from these molecules through combustion. And here's the crucial part. The products are more stable than the reactants. The total energy of the CO2 and H2O molecules is lower than the total energy of the original hexacosane and oxygen molecules. Energy has been released. This is where the heat and light come from. Specifically, the combustion of hydrocarbons releases about 42 to 47 kilojoules of energy per gram of material, depending on the exact molecular structure. For paraffin wax, it's approximately 46 kilojoules per gram. To put that in perspective, burning 1 gram of wax releases enough energy to raise the temperature of about 11 grams of water from freezing to boiling. That's quite substantial, especially considering how light and unassuming a gram of wax is. Of course, not all of this energy goes into the flame itself. Much of it radiates outward as infrared radiation, the warmth you feel when you hold your hand near a candle. Some of it heats up the candle wax below, maintaining the wax pool. Some of it escapes as visible light. The efficiency of energy conversion in a candle is actually quite low from an engineering standpoint. Only about 0.04 to 0.05% of the chemical energy is converted to visible light. The vast majority becomes heat. But for our purposes, that's perfectly acceptable. We want the warmth. We want the gentle, inefficient glow. There's something else worth noting about the chemistry: the water produced by combustion. For every 2 hydrogen atoms that burn, 1 water molecule is formed. These water molecules are gaseous at the temperature of the flame. They're water vapor, invisible. This water vapor rises with the hot combustion gases and eventually disperses into the room. You don't notice it, but a burning candle is constantly adding a tiny amount of moisture to the air. Not enough to matter in most circumstances, but it's there. The carbon dioxide, similarly, disperses into the room. 1 candle burning for a few hours will produce a very small amount of CO2, negligible in a well-ventilated space. But in theory, if you burned enough candles in a completely sealed room for long enough, you could deplete the oxygen and increase the carbon dioxide to uncomfortable levels. This isn't a practical concern for normal candle use, but it's a reminder that combustion consumes oxygen and produces CO2. The flame is, in a sense, breathing, taking in oxygen and breathing out carbon dioxide, just like we do. We've discussed the yellow glow of a candle flame, the warm light that's so distinctive and calming. But let's explore this light in a bit more depth, because it tells us a lot about the physics of thermal radiation. Light is electromagnetic radiation. It's energy propagating through space as oscillating electric and magnetic fields. Different wavelengths of electromagnetic radiation appear as different colors to our eyes. The visible spectrum ranges from about 380 nanometers, violet, to about 750 nanometers, red. Wavelengths shorter than violet are ultraviolet, X-rays, and gamma rays. Wavelengths longer than red are infrared, microwaves, and radio waves. When something is hot enough, it emits electromagnetic radiation. This is called thermal radiation, or black body radiation. The exact distribution of wavelengths emitted depends on the temperature of the object. At relatively low temperatures, say, the temperature of your body, around 37 degrees Celsius objects emit infrared radiation. You can't see it, but it's there. This is how infrared cameras can see living creatures in the dark. We're all glowing in the infrared. As temperature increases, the radiation shifts towards shorter wavelengths. Objects begin to emit visible light. First red, then orange, then yellow, then white, and eventually blue as they get hotter and hotter. This is why a piece of iron heated in a forge glows red when it's moderately hot, and yellow or white when it's extremely hot. The color is directly related to temperature. The soot particles in a candle flame are heated to around 1000 to 1200 degrees Celsius. At this temperature, they emit light primarily in the yellow to orange range of the spectrum. That's what we see as candlelight. If we could somehow make the flame hotter, if we could get those soot particles to 1000, 500, or 2000 degrees, the light would shift toward white or even blue. This is part of why gas flames, which burn hotter, can appear more blue than candle flames. Conversely, if the flame were cooler, the light would shift toward red. But there's a limit to how cool a flame can be and still be a flame. Below a certain temperature, combustion can't sustain itself. The warmth of candlelight, that yellow-orange glow, is not just aesthetically pleasing, it's informative. It tells us the approximate temperature of the luminous zone. It tells us that incomplete combustion is occurring, that soot particles are being heated and are radiating thermal energy. Compare this to a modern LED light bulb. LED bulbs produce light through a completely different mechanism, electroluminescence. Electrons move through a semiconductor material, and as they do, they release energy in the form of photons. The wavelength of these photons is determined by the band gap of the semiconductor, not by temperature. An LED can produce a warm yellow light that looks similar to a candle, but it does so without any heat. The mechanism is fundamentally different. The LED is not a thermal source. This is why LED light, despite being able to mimic candlelight in color, never quite feels the same. There's something about real thermal radiation, something about knowing that the light you're seeing is the direct result of hot particles glowing, that adds a quality to the experience. Humans have been gathering around fires for hundreds of thousands of years. Candlelight is just a controlled, domesticated version of that ancient campfire. The light from a candle flame, thermal radiation from burning carbon particles, is the same type of light our ancestors saw when they sat around fires in caves. Perhaps that's part of why candlelight is so soothing. It connects us, on some deep level, to our evolutionary past, to countless generations sitting in the dark, warmed and lit by fire. We've mentioned soot several times, but let's examine it more carefully. Soot is more than just a byproduct. It's a window into the chemistry of incomplete combustion. Soot particles are primarily composed of carbon. They form when hydrocarbon molecules don't have access to enough oxygen for complete combustion. Instead of immediately forming carbon dioxide, the carbon atoms cluster together. These clusters are tiny. A single soot particle might be on the order of 10 to 50 nanometers in diameter. That's incredibly small, tens of thousands of times smaller than the width of a human hair. At the molecular level, soot particles have a complex, disordered structure. They're not perfect crystals like diamond or graphite. Instead, they're aggregates of carbon atoms arranged in small, curved sheets. Imagine crumpled pieces of chicken wire, all tangled together. That's somewhat like the structure of a soot particle. These particles form very quickly in the hot, oxygen-poor region of the flame. Carbon atoms join together, building up larger and larger clusters. Initially, you might have just a few carbon atoms bonded in a chain or ring, but these small structures quickly grow, adding more carbon, forming larger and larger particles. As the soot particles drift through the flame, they're heated to high temperatures. This is what causes them to glow, producing the yellow light we see, but they're also being oxidized. Oxygen molecules from the surrounding air react with the carbon on the surface of the particles, slowly burning them away, turning them into carbon dioxide. Whether a soot particle makes it through the flame intact or gets completely oxidized depends on several factors. The size of the particle matters. The path it takes through the flame matters. The local oxygen concentration matters. In a well-burning candle, most soot particles are oxidized before leaving the flame. They contribute to the light output and then disappear, converted to CO2. Only a small fraction escape into the air. But if combustion is inefficient, if there's too much fuel vapor and not enough oxygen, more soot escapes. This manifests as visible smoke. Black smoke from a candle is simply soot particles that didn't get a chance to burn completely. You can see this effect if you blow out a candle. For a moment after the flame is extinguished, a thin trail of smoke rises from the wick. This smoke is unburned wax vapor and soot particles. The wax was vaporized by the residual heat in the wick, but there's no longer a flame to combust it completely, so it just drifts away as visible smoke. Interestingly, this smoke is flammable. If you've ever seen the trick where someone lights a candle by igniting the smoke trail, this is what's happening. The smoke contains combustible hydrocarbons. If you bring a flame to the smoke trail, you can ignite it, and the flame will travel down the smoke trail to the wick, relighting the candle. It's a charming demonstration of the fact that combustion isn't just about solids or liquids. It's about vapors and gases. The wax doesn't burn in its solid form. It doesn't even burn in its liquid form, really. It has to vaporize first. The flame consumes vapor. Soot, when it escapes into the air, can be a mild pollutant. It's fine particulate matter, and breathing it in large quantities isn't good for you. But the amount produced by a single candle burning in a well-ventilated room is minimal, generally not a health concern. In fact, candles are far cleaner than they used to be. Old tallow candles, made from animal fat, produced a lot more smoke and soot. They smelled worse too. Modern paraffin candles, especially those with properly sized wicks, burn quite cleanly by comparison. Beeswax candles are even cleaner. Beeswax has a different molecular composition than paraffin, and it tends to burn with less soot formation. This is part of why beeswax candles are sometimes favored for indoor use, despite being more expensive. A candle flame is never perfectly still. It flickers, it sways, it dances. This movement is not random. It's driven by air currents and the fluid dynamics of hot gases. Let's think about what's happening in the air immediately around the flame. Combustion produces hot gases, carbon dioxide, water vapor, nitrogen from the air that pass through the flame without reacting. These gases are much hotter than the surrounding air. As we know from basic physics, hot gases are less dense than cool gases. Less dense gases experience a buoyant force. Just as a balloon filled with helium rises, because helium is less dense than air. The hot combustion gases rise because they're less dense than the surrounding cooler air. So the hot gases rise rapidly upward from the flame. This creates an updraft, a column of rising gas. You can sometimes see this if there's smoke, or if you're looking at the candle in the right light. The air above the flame shimmers with heat. As the hot gases rise, they create a partial vacuum, or at least a region of lower pressure, near the base of the flame. Nature abhors a vacuum, so cooler air from the surroundings rushes in to fill this space. This incoming air provides fresh oxygen for combustion, which is necessary for the flame to keep burning. But it also creates air currents, turbulence, and these air currents cause the flame to move. If the room is perfectly still, the flame will stand relatively upright and steady. The rising hot gases create a stable column, and fresh air flows in evenly from all sides. The flame maintains its characteristic teardrop shape, but rooms are rarely perfectly still. There are drafts, however small, air currents from heating vents, from people moving, from temperature differences between different parts of the room. Even your own breathing creates small air currents. When these currents encounter the flame, they disturb the delicate balance. The flame tilts in the direction the air is flowing. The supply of oxygen becomes uneven, more on one side than the other. The flame responds by bending toward the side with more oxygen, or away from a strong wind that might blow it out. This is the flickering we see. The flame is constantly adjusting to tiny changes in the air around it, bending and swaying, trying to maintain its combustion process in the face of these disturbances. The physics of flame movement is surprisingly complex. It involves fluid dynamics, heat transfer, combustion chemistry, and gas expansion, all happening simultaneously. Scientists and engineers study flame dynamics using sophisticated computer models and high-speed cameras, trying to understand exactly how flames behave under different conditions. But you don't need any of that to appreciate the simple beauty of a flickering candle. Just watching the flame move, seeing how it responds to the air, is a lesson in fluid dynamics that's accessible to anyone. There's also something called the Coanda effect that influences flame behavior. This is the tendency of a fluid, including air, to follow a nearby surface. If there's a nearby object, say the glass of a jar candle or the side of another candle, the flame may lean toward it slightly. The hot gases are drawn to the surface, and the flame follows. This is part of why candles grouped together can interfere with each other. Each flame creates its own updraft and disturbs the air around neighboring flames. The flames may lean away from each other, or they may lean toward each other, depending on the specific air currents created. It's a subtle interaction, but it's there. We touched on the wax pool earlier, but let's examine it from a thermodynamic perspective, because understanding heat transfer helps us understand why candles behave the way they do. Heat, as we know, flows from hot regions to cold regions. It doesn't flow on its own from cold to hot. That would violate the second law of thermodynamics. So heat from the flame flows downward and outward into the cooler wax. As this heat is absorbed by the solid wax, the wax's temperature rises. When it reaches the melting point, something interesting happens. The temperature stops rising temporarily. This is because melting requires energy, but not to increase temperature. Instead, the energy goes into overcoming the intermolecular forces holding the wax molecules in their solid arrangement. This energy is called the heat of fusion, or enthalpy of melting. For paraffin wax, the heat of fusion is around 200 to 250 joules per gram. That means you need to add 200 to 250 joules of energy to melt 1 gram of paraffin, even if it's already at the melting point temperature. So as the flame heats the wax, the surface layer reaches the melting point and starts to turn liquid. But this process absorbs energy, which temporarily slows down the heating of the wax just below the surface. It's like a thermal buffer. Eventually, enough heat is supplied that a layer of wax melts. This liquid wax then acts as a heat transfer medium itself. Heat conducts through the liquid more effectively than through solid wax in some ways, because the liquid can also circulate via convection. The depth of the wax pool reaches an equilibrium. Heat input from the flame versus heat loss to the surrounding solid wax and to the environment balance out. A deeper pool has more thermal mass more liquid that needs to stay molten. If the flame can't supply enough heat, the pool won't get too deep. If the flame is very hot, the pool can be deeper. Candle designers have to consider this carefully. A jar candle, for instance, retains heat better than a freestanding candle because the glass walls insulate the wax. This can lead to a deeper, hotter wax pool. The wick size has to be chosen accordingly, or else the pool might get too deep and drown the wick. A freestanding candle loses more heat to the surrounding air through convection and radiation. The wax pool will generally be shallower. This is fine, as long as it's still deep enough to provide consistent wicking. Temperature gradients in the wax are also worth considering. Right at the base of the wick, the wax might be nearly 100 degrees Celsius or more. Just a few centimeters away, it might be only 50 degrees. This gradient drives convection within the pool, as we discussed before. Below the pool, in the solid wax, there's also a temperature gradient. The top layer, just beneath the liquid, is close to the melting point. Deeper down, the wax gets progressively cooler, eventually reaching room temperature at the bottom of the candle. Heat conducts through this solid wax, slowly warming the material ahead of the melting front. This preheating makes melting more efficient, but it also means that a candle's burn rate can be influenced by the ambient temperature. A candle in a warm room might burn slightly faster than the same candle in a cold room because the wax is already warmer and requires less energy to reach the melting point. All of these thermal considerations combine to determine how a candle burns, how long it lasts, how large the flame is, how much soot it produces. It's a delicate balance, one that candle makers have been refining for centuries, largely through trial and error. Many modern candles are scented. They contain fragrance oils that evaporate along with the wax vapor, filling the room with pleasant aromas. Let's explore how this works. Fragrance oils are mixtures of various organic compounds. These might include esters, aldehydes, terpenes, and many others. Each compound has its own scent profile, and by mixing them in different proportions, candle makers can create complex, layered fragrances. These fragrance compounds are dissolved in the candle wax when the candle is made. As the candle burns and the wax melts, the fragrance compounds are released. Some fragrance molecules evaporate from the hot wax pool. The heat of the liquid wax provides enough energy for these molecules to break free from the wax and enter the air. You can smell the candle even before the fragrance reaches the flame. Other fragrance molecules are drawn up the wick along with the melted wax. They vaporize in the heat of the flame. Some may even undergo partial combustion, though this is generally avoided by using heat-stable fragrance compounds. The key to a good scented candle is balance. Too little fragrance, and the scent is weak. Too much, and it can interfere with the burning process. Fragrance oils can change the viscosity of the melted wax, affecting how well it wicks. They can also affect the flash point, the temperature at which vapors can ignite. Most scented candles contain around 5 to 10% fragrance oil by weight. This is enough to provide a noticeable scent without causing burn quality issues. Fragrance, through the term for how well a scent spreads through a room, depends on several factors. The type of wax matters. Soy wax, for instance, tends to hold fragrance well, but releases it slowly, giving a more subtle scent. Paraffin wax often provides stronger fragrance throw. The size of the room matters, obviously. A small room will fill with scent more quickly and intensely than a large room. Air circulation matters. If air is moving, it carries the fragrance molecules with it, distributing them more evenly and quickly. In a still room, the fragrance might linger near the candle, and the fragrance compounds themselves matter. Some molecules are more volatile, meaning they evaporate more readily. These provide immediate scent when the candle is lit. Other molecules are less volatile and provide longer-lasting, more subtle background notes. Perfumers and fragrance designers talk about top notes, middle notes, and base notes. Top notes are the light, volatile compounds you smell first. Middle notes emerge as the candle burns. Base notes are the heavy, lingering scents that last longest. A well-designed scented candle balances these notes, creating an evolving fragrance experience over the course of the burn. There's also the question of how fragrance interacts with our psychology. Certain scents are universally pleasing or calming. Lavender, for instance, is known for its relaxing properties. Vanilla is comforting. Citrus scents are energizing. But scent preferences are also highly personal and culturally influenced. A fragrance that one person finds delightful might be cloying to another, and scent is strongly linked to memory. A particular fragrance might evoke powerful associations, positive or negative. This is why there's such a vast market for scented candles with countless different fragrances. People seek out scents that resonate with them, that create the atmosphere they want in their homes. From a pure chemistry standpoint, though, scented candles are simply a clever way of using heat to volatilize pleasant-smelling organic compounds. The candle flame provides the energy, and the air circulation distributes the molecules. It's a functional application of chemistry and physics to create a sensory experience. Every candle begins in an unlit state and, eventually, ends as a puddle of solidified wax, a nub, or just memories of warm light. Let's follow this life cycle. When a candle is first made, whether by hand or in a factory, hot liquid wax is poured around a wick. The wax cools and solidifies. The candle takes its shape, determined by the mold or container used. At this stage, the candle is potential. All of its chemical energy is stored in the hydrocarbon bonds, waiting to be released. The wick is dormant, just a piece of cotton or another material, serving no purpose yet. Then comes the first lighting. A match or lighter is applied. The wick ignites. The cycle of melting, wicking, vaporizing, and combusting begins. The candle has come to life, in a sense. Over the hours of its first burn, the wax pool forms. The candle finds its equilibrium. If it's well made, it burns evenly, the wax pool extending to the edges. The flame is steady, bright, and clean. After a few hours, the candle is extinguished. The wax pool solidifies. The candle sits, waiting for the next lighting, slightly shorter than before. With each successive burn, the candle gets smaller. The wax is consumed. The chemical energy stored in those hydrocarbon bonds has been released as heat and light. The carbon has been oxidized to carbon dioxide. The hydrogen has combined with oxygen to form water. These products have dispersed into the atmosphere. Eventually, only a small amount of wax remains. The wick is short. Lighting the candle again might result in a weak flame or no flame at all. The candle has reached the end of its functional life. What remains? If it was a container candle, there might be a thin layer of wax at the bottom, not enough to sustain a flame. If it was a freestanding candle, perhaps just a small puddle or nub. This final remnant contains the same chemical composition as the original candle, just far less of it. In theory, you could melt it down and reform it into a new candle, though it would be quite small. Some people do this, collecting candle remnants and reusing the wax. From a thermodynamic perspective, the candle's journey is one of entropy increase. The ordered structure of the solid wax has been disrupted. The chemical bonds have been broken. The energy has been dispersed into the environment as heat, which has spread out and dissipated. The carbon and hydrogen that were once part of the candle are now molecules of CO2 and H2O, mixed into the vast reservoir of Earth's atmosphere. This is the story of all combustion, really. Order to disorder. Stored energy to dispersed energy. The second law of thermodynamics in action. But while it burned, the candle provided light and warmth. It created atmosphere. It served its purpose. And in that sense, the candle's life cycle is meaningful, even though it ends in its own consumption. Humans have been using candles, or candle-like devices, for thousands of years. The history of the candle is intertwined with the history of civilization itself. The earliest candles were probably very simple. Perhaps a piece of rope or reed soaked in animal fat or oil. Light it, and you have a flame. It's not elegant, but it works. Ancient Egyptians used rushlights, reeds soaked in animal fat. The Romans developed candles more similar to what we'd recognize, using tallow, rendered animal fat, and wicks made of rolled papyrus. Beeswax candles appeared later. They burned cleaner and smelled better than tallow, but they were expensive. Only the wealthy or the church could afford them in large quantities. For most of history, beeswax candles were a luxury. The Middle Ages saw candle making become a recognized craft. Chandler's candle makers formed guilds. They developed techniques for improving candle quality, like dipping wicks repeatedly in melted tallow to build up layers of wax. In the 18th century, spermaceti wax, derived from sperm whales, was introduced. It produced bright, odorless candles, but it was even more expensive than beeswax, and its production contributed to the decimation of whale populations. The 19th century brought major changes. Stearin, a substance derived from animal fats, was discovered to make better candles than pure tallow. Around the same time, paraffin wax was isolated from petroleum. It was cheap, abundant, and burned well. By the end of the 19th century, paraffin had become the dominant candle-making material. This period also saw improvements in wicks. Braided wicks that curled as they burned were developed, reducing the need for manual trimming. Mechanization made candles cheaper and more accessible to everyone. And then, electric lighting arrived. Suddenly, candles were no longer necessary for illumination. By the early 20th century, electric lights had largely replaced candles for practical purposes in developed countries. But candles didn't disappear. Instead, their role changed. They became decorative, atmospheric, ceremonial. People burned candles because they liked the soft light, the ambience, not because they needed the illumination. Today, candles are a global industry worth billions. We have scented candles, decorative candles, candles for aromatherapy, candles for religious ceremonies, candles for emergencies. The candle has evolved from a necessity to a lifestyle product. Yet the basic principle remains the same as it was thousands of years ago. A wick, some form of wax or oil, and fire. The chemistry hasn't changed. We're still oxidizing hydrocarbons for light and heat. There's something profound in that continuity. In a world of rapid technological change, the candle remains essentially unchanged. It connects us to our ancestors, who sat in the dark with their tallow candles, just as we sit in our homes with our paraffin or soy candles. The flame is the same. The comfort it provides is the same. Before we conclude, it's worth discussing safety, because fire, even in the controlled form of a candle, demands respect. A candle flame is hot. We've mentioned temperatures of 1000 to 1400 degrees Celsius or more. That's hot enough to ignite many common materials: paper, fabric, wood, even some plastics. The most important safety rule is simple: never leave a burning candle unattended. It's easy to forget a candle is lit, to walk away, to become distracted. But a candle flame is a constant ignition source. If something flammable comes into contact with it, a fire can start. Candles should always be placed on stable, heat-resistant surfaces. The wax can melt and flow. If the candle is on an unstable or flammable surface, this can lead to problems. A tipped candle can spill hot wax, and the flame can ignite whatever it falls onto. Drafts are also a concern. A strong draft can blow a flame into contact with nearby objects, or it can cause the candle to burn unevenly, potentially leading to the glass container cracking, in the case of container candles, or the flame growing too large. Trimming the wick is important for more than just aesthetics. A long wick creates a large flame, which can be a fire hazard. It also produces more soot. Most candle makers recommend trimming the wick to about 1/4 inch, about 6 millimeters, before each lighting. Container candles have their own considerations. Never let the wax pool get too deep, as this can cause overheating. Don't burn the candle all the way down to the bottom stop when there's about 1/2 inch of wax left. The heat can build up in the glass at the bottom, potentially causing it to crack. And of course, always extinguish candles before leaving a room or going to sleep. You can blow them out, though this can create smoke. A candle snuffer is gentler. It starves the flame of oxygen without creating turbulence. With proper care and attention, candles are quite safe. Millions of people burn candles every day without incident. But the potential for harm is there, and it's important to be mindful. In recent years, alternatives to traditional paraffin candles have become popular, each with its own characteristics. Soy wax candles are made from hydrogenated soybean oil. Soy wax is a renewable resource, unlike petroleum-derived paraffin. it tends to burn cooler and slower than paraffin. Soy candles are often marketed as more natural or eco-friendly. From a chemical standpoint, soy wax is also a mixture of hydrocarbons, though with slightly different molecular structures than paraffin. The combustion process is essentially the same. You're still oxidizing carbon and hydrogen to produce CO2, H2O, heat, and light. Beeswax candles, as mentioned, have been around for a very long time. Beeswax is a natural wax produced by honeybees. It has a higher melting point than paraffin, around 62 to 64 degrees Celsius. Beeswax candles often burn brighter and cleaner than paraffin. Palm wax is another alternative, derived from palm oil. It creates interesting crystalline patterns when it solidifies. Coconut wax is newer, made from the meat of coconuts. There are also gel candles, which use a gel made of mineral oil and a polymer resin instead of traditional wax. These have a transparent appearance and can have objects embedded in them for decorative effect. Each of these alternatives burns according to the same basic principles we've discussed. There are variations in melting point, burning temperature, soot production, and scent, but the fundamental chemistry of combustion remains unchanged. Some people prefer natural waxes for environmental or health reasons. The evidence on whether paraffin candles pose any meaningful health risk from normal use is mixed. Most studies suggest that burning candles in a well-ventilated space produces minimal indoor air pollution. But natural waxes offer peace of mind to those concerned about petroleum products. From a pure science standpoint, what matters most is proper burning. A well-made paraffin candle, burned correctly, is clean and safe. A poorly made soy candle, burned incorrectly, can produce excess soot and smoke. The material matters less than the design and usage. Let's return, in closing, to the simple pleasure of watching a candle burn. There's an aesthetic dimension to candlelight that goes beyond its function. The way the flame moves, the soft glow, the interplay of light and shadow in a room lit only by candles. Artists have long recognized the special quality of candlelight. Paintings from the Renaissance and Baroque periods often depict scenes lit by candles or oil lamps. The artists understood how to render the warm light, the soft gradations from brightness to shadow. Photographers, too, appreciate candlelight. It provides a soft, flattering light that's difficult to replicate with electric sources. The color temperature of candlelight is around 1,800 to 2,000 Kelvin, much warmer than most indoor lighting, which is typically 2,700 to 6,500 Kelvin. This warm color temperature is part of why candlelight feels cozy and intimate. It's associated with evening, with relaxation, with the end of the day when the sun's warm light has faded. There's also the psychological effect of the flame itself. Humans are drawn to fire. We've evolved alongside it. The sight of a flame can be calming, meditative. There's a gentle randomness to its movement, a visual interest without being overstimulating. This is part of why watching a candle burn can be an aid to sleep or relaxation. Your mind has something to focus on, something mildly engaging, but not demanding. It's similar to watching waves on a beach or leaves rustling in the wind. Natural, repetitive, calming. The candle doesn't ask anything of you. It simply burns. It transforms wax into light, slowly, steadily, patiently. And in that transformation, there's a kind of beauty. And so, we've come to the end of our journey. From the unlit candle, through ignition, through the chemistry of combustion, through the physics of flame, through history and safety and alternatives, we've explored what it means for a candle to burn. It's a simple thing. A candle, wax and wick and flame. You can buy one for $1 at a store. You can make one yourself with materials from your kitchen. It's humble, unassuming, but within that simplicity lies remarkable complexity. Chemistry, physics, thermodynamics, fluid dynamics, all working together, all in balance, all contributing to that gentle glow. The next time you light a candle, perhaps you'll see it a bit differently. Perhaps you'll appreciate the wax pool forming, the way the wick draws up liquid fuel, the zones within the flame, the thermal radiation producing that warm yellow light. Or perhaps you'll just enjoy the candle for what it is, a source of light and comfort, a small act of transformation, a moment of calm in a busy world. Either way, the candle will continue to burn, as candles have burned for thousands of years. Patient, steady, illuminating the darkness, one molecule at a time. And that, really, is beautiful in itself. Thank you for watching. Rest well.